Merci, Pierre. I have to apologize right away for speaking English. My French is just too bad. We can do that in German also, if you like. No? Okay. So, thank you very much for the introduction. Yeah, I've been asked to give this talk, a rather brief talk today. I hope I can manage within half an hour because there's so many stories to tell. Yeah, so you have to stop me as soon as I start babbling away. Within sort of the context of a BIM course, so I decided to entitle this BIM to Fabrication with a big question mark behind it. And I'll try to explain why that is the case. First, I mean, Pierre has already mentioned it. I'm the co-founder of DesignToProduction with offices in Zurich and in Stuttgart, which is sort of a consultancy that helps architects, engineers, fabricators, everybody else involved in building complex architectural projects. Complex means mostly complex geometry, like all this curvy stuff you see there. We also had a few non-curved projects that for other reasons were complex. But mostly we have to deal with these funny shapes here. And what we do is that we sort of sit in the middle between everybody and try to get the information from A to B without any loss. And I'll explain how that works by a few examples. This is the project where everything started with. I was working as a research assistant at the ETH in Zurich for a couple of years for Professor Ludger Hovestadt at the Chair for Computer-Aided Architectural Design. And in 2005, we were asked to build a pavilion to basically show the possibilities of the digital chain, which means a completely digital process from design into fabrication. By example of this little sphere with about 4 meters diameter that was built from 320, I think, all quadrilateral frames. So each of those parts, each of these components only has 4 boards. Every component is basically completely the same, only that they have different shapes. But it's really just 2 cuts with a radius, 2 cuts with a mitre, 2 drilling holes and 2 notches where you can drive in little dovetail connectors in the corners to build those quadrilateral frames, which are nicely numbered. And if you stack them one on top of the other in the right order, you get this nice little sphere. And that was the trick, had those rectangular or actually quadratic openings there. And this little mesh had to align itself with the openings. That was my part of the thing. I was responsible for sort of the design optimization. And a colleague of mine was responsible then to get this design onto a 5-axis CNC milling machine at the carpentry that would do all those 1,500 almost little wooden boards. And that, for the first time, when I realized, coming from the computer science side of things, that despite all the promises that the software industry is making all the time, there's a huge gap between those 2 parts of the process. So it's not like you send the file to the fabricator, he puts it in the machine, and then it gets done, but it's different. So this, for me, was sort of the start of the whole venture. We also worked on this project here, which you probably know, at the very end of the food chain, I have to admit, because what we did is we built or planned the formwork for this huge undulating concrete slab where the Rolex Learning Center is standing on top of. Basically, by designing about 10,000 of those vertical plywood cleats there, which were 4-axis cut in Germany, then shipped to close by Bern, where the formwork contractor took 6 or 7 of them and nailed them together to boxes, shipped those 1,500 boxes here to the EPFL site, put them on top of standard scaffolding towers, actually, to get this formwork for the concrete slab that you're now walking on if you are studying in the Rolex Learning Center. This is where you can see the whole area. On the right-hand side, there's still the scaffolding towers, adjusted to within 2 or 3 millimeters height where they should be. Then the boxes are put on top of them, and on the right side there's already the rebars in there, the reinforcement for the concrete. And as you can see, there's pretty much steel in this concrete slab. Remember the next time when you walk on that. This basically was our first timber building. Only that there's no timber building anymore. It's all been taken away again, and as they say, thermally recycled. But that gave us an idea about what would be possible on a larger scale, especially in timber. And our next timber building was this one, where we worked for a German timber contractor, Holzbau Ammann, in the Black Forest, to get this wooden roof for the Centre Pompidou in Metz, designed by Shigeru Ban. Right, this is 7,500 square meters, as I said, of basically a straw hat was the image that Shigeru Ban apparently had in mind. At least they exhibit this straw hat proudly in the Centre Pompidou. I think it's still there. It was in the information center. There was this Chinese straw hat. Only that the straws in this straw hat are timber beams with a cross-section of 14 by 44 centimeters, or roughly like that, which means they're pretty stiff and it's pretty hard to actually weave them into a straw hat. They're all pre-cut into the right shape on five-axis, large-scale five-axis CNC machines. So there's 1,800 of those things. They're on average 10 meters long. All the connection details are already in to put them together on site. So
black marks a numbering system? Or?
This black marks this is not a numbering system yet, but the number is actually on the other side. This is marking which end that is. There's either two lines here or just one line, which tells you is it the front or the end of the beam. Yeah. Down here you can see the number if you look closely. There in the corner there.
It's not an effect of the optics of the photograph. They are non-planar.
They're definitely non-planar, yeah. I mean, they're all doubly curved. Basically, they're following, and I'll show this later on, they're following a NURB surface, also an orientation along the beam.
So I do not know if you want us to already start with the question. Perhaps it's
Anytime. We'll just not be able to make it in 30 minutes, but if you have time, please interrupt me anytime you like. So this is, I mean, you've seen this picture already. This is what it looks like. In the end, there's 3 directions of beams, and you have 2 parallel girders running in each direction with shear blocks in between so that you get a stiff girder. And you have always 4 beams crossing in one point, 2 directions. And the connection is done with hardwood pins that are glued. You can see that here, glued into the beam. So there's sort of an hexagonal cutout in the beam where you glue in this hardwood pin, and then those are stacked on top of each other at the crossings and tightened with a threaded rod, pre-stressed, so that you have a good connection there. And then the last project I very briefly show is this facade in Norway, in Kristiansand, for the Kilden Performing Arts Center, designed by ALA architects from Helsinki. The building itself is actually a concrete box, which you can't see anymore. There's this facade to the water side of the Kristiansand harbor. The upper edge is straight, 100 meters long. And then you have a curvy edge on the floor, and the straight beams or straight boards, oak boards actually, connecting them from bottom to top. There's about 3,500 square meters. The image, of course, is a curtain blowing away in the wind, and the idea was, or one of the design ideas was, to have those oak boards running down the facade with 10 millimeter straight gaps in between them from the tip down to the ground. The boards start at 120 millimeter width at the floor, and then get, of course, narrower and narrower to the top, because the straight line on the edge is shorter than the curved line on the floor. And the tricky part here was to really get the precision that was required to get those straight 10 millimeter gaps running up the facade in a straight line. It was broken down into 126 facade elements that were prefabricated in a boat builder's, a wooden boat builder's workshop about 100 kilometers from the building site. Luckily, we had the building site right at the water, and we were assembling or pre-assembling in a boat workshop, so we could literally ship 50 square meter large elements directly to the construction site and hoist them up into the facade. So there's always 2 straight beams on either side of the element and then a number of curved beams, and up to 180 oak boards on each of those elements. Inside, there's also a bit of build-up, mainly for acoustics on the inside of the foyer side of the glass facade. On the outside, it's pretty much open. It's basically just a weathering facade there. So those are being pre-assembled, then shipped to the facade, and hoisted into a steel construction that is holding up the whole thing one by one. During construction, looks like this. The black gaps here is where still a few cladding boards are missing, so that you can still reach the tightening points where the elements are fixed to the steel structure.
So the steel structure is planar?
The steel structure is not planar, but that's straight I-beams actually going down at the right angle. So it follows the geometry of the facade. So the trick is really to have straight lines going down the facade everywhere. I can tell you another story about that. It was not so easy to get there.
So you designed the wood, but the steel system was made by someone else?
The steel system was made by someone else. Actually, it was already planned before we entered the project. This is another long story. In many of the projects, we come in a bit late, sometimes even when the whole thing is more or less on fire already, and then we have to find a way of getting things done that have been planned in a different way. In this case, the building was already out of the ground. The steel structure was planned but not built yet when we got into the project together with a Norwegian timber contractor and a Swiss timber engineer, and then sort of had to change the construction principle of the facade a bit. Which was tight because they wanted to set up the steel frame when we didn't have any 3D model or plans of the facade yet. So we had to decide where to drill the holes for connecting the timber elements before we had the timber elements. Happens. This is the building industry. Welcome.
Could you use the geometry of the plans, or did you have to do another survey of the?
In this case, what we got, I mean, this is Norway, this is Scandinavia. You have a BIM model of the whole thing, excluding the facade, because the facade is curved and the BIM software can't do any proper curves. So you had a BIM model where already the steel beams, the whole steel construction, actually the steel construction won the Finnish steel prize. Can't see any of it anymore. Anyway. And we had a design surface by the architects, which was almost all right to do the planning on top of that. And then basically we had to put 2 things together. First thing, by coming up with proper details together with the timber engineers that would allow us to take the plus minus 50 millimeter tolerance that were in the steel structure down to plus minus 1 millimeter that we needed in the facade to get those gaps running in straight lines, and a few other things. It is a ruled surface, yeah. Yes. That's the whole point. With a few tricks that they tried to play and had to then take back, but I'll come to that in a minute. So the end result looks like that. Went out pretty well. The architects were a bit disappointed in the first place, where we came up and said we can't assemble this on site. We have to prefabricate in elements, which means you have those lines in the other direction 2 every 7 meters or so. Sort of disappointment, of course, but then it was luckily possible to explain why. And I think it still looks pretty good. There's another image coming up. There's a few other things. This one has just been finished not too far from here in Roll, down at the lake. A concert performing arts center again by Bernard Tschumi. I thought that would be a public building when I got into the project, until I found out it's basically the performing arts center of the world's most expensive boarding school at the lakes, at the shores of Lake Geneva. So they built a 5 million Bernard Tschumi performing arts center there on the Green Meadow. I don't think you can get in, but if you drive by, you can have a look at it. It looks really beautiful. You don't see the timber structure there anymore, because basically this is cladded with stainless steel now. So it's very shiny and bright. Have a look at it. Right now on the machine, not too far from here too, on the other side of the hill in France, is basically the basement of the pavilion, the French pavilion for the Expo in Milan next year, by Extu Architect.
Do you know already who will be the carpenter for doing this?
Yeah, it's on the first piece. I got a picture yesterday with the first pieces on site, so it's already being assembled there.
Who is the carpenter?
Simona. Simona. And right now we are working on this project a bit too. That's the new headquarters for Swatch in Biel by Shigeru Ban again. This is one of the very few projects where we are involved pre-tender already. Usually we're really only working for the fabricators at the end, because no one thinks of asking us good questions before that. This is one of the good exceptions where we were able to infuse some knowledge before the thing went out into tender. They're building a mock-up right now in Biel, and the whole thing is probably going to start construction end of next year. So what's it all about? It's all about workflow, basically, what we're doing. It's all about putting things together in a proper way. Everything we do is basically about prefabricated components. This is from a project I haven't shown yet, but it tells you a bit about the complexity of the components that are being fabricated and put together, like an IKEA shelf, basically, on site. So the complexity is actually put into the components off-site, like here. The idea is to have the dowels and the screws in the right place, because there's a drilling hole for them. If you can read the assembly instructions, you can probably put together this Billy shelf in 15 minutes. At least if you have moved a couple of times during the last 5 or 10 years. And that's basically the same that we're trying to do, is to put the complexity into the components and handle it off-site and not on-site. Of course, this is only possible by using CNC fabrication. We're doing sort of a mass customization that would be called in the consumer goods industry. Yeah? In the internet, you can type in a few measurements and swipe the credit card, and then your tailor-made shirt arrives a week later. This is what we're doing with those projects. Those 3,500 components there on the right-hand side that are being assembled to the roof of a golf club in South Korea are actually all different, but they're all the same. They're geometrically different, but they all follow the same rules. They're all fabricated the same way. And our task in those projects is to set up sort of a fabrication chain that would allow us to mass customize those components. And fortunately, we're working in architecture. That means we don't have to find 3,500 clients to buy one of those. We have to find one client that buys 3,500 of those, which means investing a few weeks into engineering and even software development in the beginning actually pays off within one project. We're actually developing a complete fabrication chain, including the software that does the planning for the project, and then we throw it away afterwards. Yeah, not the machine that's doing that, but the software that's doing the planning.
I understood during a visit in Amman that they have to change all the electronics because of the
to increase the speed of fabrication. You are talking about this software to also doing the fabrication, or only the software for designing?
We are actually, it's about the interface between the designing and the machine. So someone has to translate the geometry that comes out of whatever design software you have into control commands that the CNC machine is reading, which means usually actually NC code that only holds X, Y, Z, A, B coordinates for the 5 axes of the machine, or how many ever axes you have. And the translation between one and the other is something that is tricky as soon as you go away from standard components. I'll come back to that in a minute. Yeah. So what we exploit is the ability of this machine to do very precise components at very high speed, especially in timber, which is a very nice material to CNC fabricate, because you can cut it in a very precise and quick way, as opposed to steel beams, for example. And you can also prefabricate all the connection details directly in the component, as opposed to steel beams, for example. Usually you have to weld flanges and other things in there, which then messes up the precision completely, and so on. And the machine doesn't care if it's doing 1,000 different or 1,000 similar pieces. Yeah, it's really just about the input for the machine, the data the machine needs to do this. So the workflow that we're using basically is the usual design, planning, building thing. Yeah. Only that we split the last part into fabrication and assembly. So there's not so much building, there's more assembly on site, which means there's a fabrication part off-site. And sometimes there's even a pre-assembly off-site, like in the Norwegian project, where you have large chunks of the building, 50 square meter chunks of the facade, pre-assembled off-site and then shipped to the site and put together there. Which means actually you have a lot more planning in there and a lot less assembly on site in the process. And that comes from having more individual parts, which means someone has to basically draw workshop drawings for every single one of those 12,500 cladding boards that are in the facade. And on the other side, you have a much increased level of detail that you have to care about. Every single one of those 12,500 cladding boards has about 10 drilling holes and a few 5-axis cuts in there to fit precisely at the given place into the facade, that all have to be in the model. So what we're doing is we are actually the ones sitting in the middle of this triangle between the architect, the engineer, and the fabricator, building a parametric 3D model of the whole thing, which is absolutely necessary because I don't want to draw those workshop drawings by hand. I want to come up with the rules, program instead of drawing. We take sort of the design as a reference, geometry as an input that tells us, okay, the overall shape of the thing is like that. We issue models and data to the engineer so that they can do their calculations. And in the end, we issue fabrication information that might be actual G-code driving the machine in some projects. In most of the projects, it's on a rather higher abstraction level than that, because we don't know the machine, and it only makes sense for very high numbers of components to really build your own post-processor to generate G-code directly to the machine. Usually we're issuing 3D models with extra geometry that would tell the fabricators what to do, and then on their side they also do some programming scripting in their CAM software to come up with the actual machining code in the end. But that's only half of the story. The other half of the story, of course, is to do this parametric model, we also need to know about the details and the dimensions coming from the engineering side. So we have to talk very closely to them. Okay, what is your detail? Your standard detail looks like this, but we have to basically apply this to 2,500 different connections in the whole facade that are geometrically all different. So is it working in every single place? is more like a controller job on our side mostly, that says, okay, you give us your detail. Mostly they draw rectangular things where everything meets perfectly orthogonal in the node, and then you say this is the only situation that you don't have in the whole facade. Yeah, there's no right angle in there. Everything is slightly skewed, rotated, whatever. So we have to then translate this into a parametric detail and check this against the geometry of all the 2,500 nodes in there if it's really working. And the other thing is that we have to know about the fabrication methods that are used. Can we actually fabricate these details on the given machine with the given material? And those two little circles, loops down there, are rotating quite heavily in every project. The goal, of course, would be to have this information going up to the architect and the designer too. So what are your dimensions, what are your details like that hold up the whole thing? What is the fabrication method? What can we do or can't we do to already know about this at the design stage and design accordingly, design for assembly. Yeah. This proves to be a very hard problem to tackle for various reasons, mainly because architects are not paid to take care of that, which means they cannot pay us to tell them about, and they cannot pay a fabricator to tell them the secrets early on in the project. So there's a process problem there at the moment, which you can probably change. I hope so. We try to help you anytime. So very quickly about the challenges in the process. There are quite a few, and the process one is only one of them. Yeah. We have to tackle a lot of different components in the project. But usually we start with sort of a design input, and the design input has to match the fabrication tolerances already. Because in the end, you're taking a machine like this. This planing tool has a diameter of 40 centimeters, just to give you an impression, and works on a 10-meter long beam, and is able to fabricate this beam within tolerances of some 1/10 of a millimeter, which is not just some Swiss precision fetish that we're all following. It's very necessary if you want to fabricate the connection details directly on the machine. If you're having a slotted plate with steel dowels in place, there is a code, a standard somewhere that tells you what precision you have to drill those dowel holes in order to get the thing ticked off by the control engineer in the end. And this is, I think, in the SIA norm, it's about 3 or 4/10 of a millimeter. Yeah, so you need this precision actually not to get the connections right in the end, which means you have to provide fabrication data that's precise within 1/10 of a millimeter, which means if you're taking the input from an architect or engineer to feed into your parametric model, even that has to be precise by 1/10 of a millimeter, because after that, the errors just multiply. Yeah? You never get the information back once you threw it away. Yeah, this. If you have, yeah.
Does it mean that you surface the wood before machining? Because the main problem you can get with the wood, this is the deformation of wood, so the reference can be not the right one.
In this case, it's so that this geometry of these beams is cut out of sort of a blank. You can see that here. So the actual timber piece is 20 millimeters bigger than the final thing, and you plane it out. Of course, you have the same tolerance problems that you have everywhere. I mean, timber is reacting to moisture, steel is reacting to temperature more than timber, and vice versa. So you always have to care about sort of environmental conditions during fabrication, assembly, and later on also. All building materials are moving somehow, expanding, shrinking, bending, being elastic or whatever.
So how do you just control the climates within the wall, or you maintain the piece with steel, for instance, steel frames?
No, the conditions in the fabrication are controlled in any timber fabrication where you go. I mean, we're usually working at a certain temperature range and a certain moisture range. There, the things are more or less shrink wrapped when they are sent to the construction site, and they also sometimes even have to be controlled on the construction site, especially when you try to glue things on site. It has to be in a controlled environment. But that's actually not the problem in most of the case. So the deviations you get from shrinking and swelling due to moisture and timber is something that's so well known to timber engineers that the connection details are actually done in a way that they can handle this. Yeah, that's not the problem.
For these edges, there was regular screws or bolts put in.
Yeah, this is really just a standard steel plate with steel dowels holding them together. This is one of the beams of the Centre Pompidou. This is sort of the...
Not self-drilling, but...
no,
regular bolts.
they're just regular steel dowels, then banged in.
Is there like a kind of gap in between the bolt and the hole? Is the hole larger than the bolt by more than like a millimeter?
It's actually pretty precise. This is one of the precision things that I was talking about. So this hole has to have the precise diameter, which is not a problem because you have a drill that's usually has a certain diameter, but it has to be positioned within a few tenths of a millimeter to meet the holes in the steel plate and to actually being able to transfer the loads.
For the hexagonal thing, you also had like literally no tolerances. It
Yeah.
was like
What dimensions are we looking at? Thicknesses?
The beam is 14 by 44 centimeters. The dowels, I can't really tell, but roughly 12 millimeters about. Steel plates probably 6 to 8 to 10 millimeters, depending on where they are and how bad the loading is. And there you can see, basically there you can see the numbering system. So this is a beam on axis 61. I can't remember, it's 7 years ago. So there's axis 61, it's beam segment number 60 in the 4th layer, something like that. So once you remember how to read this numbering system, you basically know where the thing is in the roof.
How do you manage just simply the load out of all these numbers and all these places? You get thousands of different numbers.
Basically, that's one of the first things that we have to do early on in the project together with everyone, is to come up with a reasonable numbering system that is not only machine readable, but mostly also human readable. Yeah, someone has to understand how things are working.
You put it on the trucks in a certain order.
That's another thing then. I mean, there is sort of an unambiguous naming and numbering system for all the components in there. And then you have to take care of the, basically go backwards from the assembly sequence that is needed for whatever reason. And then go backwards basically until the ordering of the raw material to get the sequencing right. So there's very few places where you can store. I think in the end it was net about 1,000 cubic meters of timber there where you can really store that. So you have to sort of work in the right schedule and fabricate in time, just in time for the assembly. Yeah, this is the straw hat, the literal thing. And that's the problem then. I mean, you know that you have to be precise within a few tenths of a millimeter, then you get the straw hat. And then you get, or the timber fabricator gets a DXF file with nodes and straight lines in there. That's the basis for fabrication, and that happens. I still don't know where this model in this case came from. Actually, I suspect it comes from the structural engineers. But in the end, you can't use it for fabrication, no way. I mean, the thing that Shigeru Ban doesn't want to see is a beam with a kink at every node. He wants to have a continuously curved beam. So the first stage in almost every project is to take whatever input you get and redesign a proper design surface, in this case a NURB surface, that defines not only the location of every point in the roof, but also the orientation of every point. In this case, the normal direction on the surface. That would also define the orientation of the beam and also defines the orientation of the connection nodes in there. And has to be precise. In this case, we actually had to find someone who's working for the automotive industries mainly to reconstruct proper NURB surface from point clouds to get this surface. Because as you can imagine, it's a bit tricky. The surface actually continues across this hole. So it's making an S-curve in here. It's got very, very bad angles there, and it goes down into those funnels. And still has to be curvature continuous. And then, yeah.
Is this a mesh finally, or is
no? This is a NURB surface.
But for smoothing, they probably use mesh algorithms.
I guess that that was our first guess too when we saw this. Yeah, that someone did a bit of I don't know, relaxation there to smooth things out. We tried to do the same thing because the input wasn't smooth at all. And then it turned out that if you relax that, then it comes out too deep in the back to fit the HVAC underneath. So basically, someone already has designed this by pushing around nodes and making it worse. So that's actually the tricky bit. And then from there on, you can set up a parametric software, parametric model, to then really get the thing down to the last drilling hole. We had another Shigeru 1 project that I haven't shown yet, where we didn't have this problem. This golf club in South Korea that I already mentioned has also prefabricated elements on site where we had no 3D model in the beginning, but basically a napkin sketch that would tell us, okay, there's a regular grid of 9 by 9 meters. You have to be horizontal along this line. You have to be at a certain angle at this line. And then from there on to set up a proper design geometry is much easier than to take a point cloud with 2,000 points and re-engineer things. Also, always interesting in the discussion there.
So are those elements in the last one, are they milled from like laminates or?
No, they're also milled from glue lam beams. So this is beam segments that are put together to form this. I mean, this element has a footprint of 9 by 9 meters, and is
kind of a passive version together, and then mill that to
no.
smooth.
No, not possible. I mean, this is roughly altogether. It is about 2,500 square meters. You would mill away 80% of that if you do that this way. And you'd have problems actually getting the thing laminated because the curvature is so high that your layers have to be very thin because it's a doubly curved surface. Also, you had to come up with, it doesn't really work. Yeah. You need a very big pressing. I mean, this is in furniture, that would be in a natural way. You have very thin layers of veneer. You put them together with glue in between and a pressing bed, push them, and then you get something like this here. Yeah. But it's going to be rather hard to get a pressing bed with 81 square meters.
So what's your, like, how did you do it?
They were actually fabricated the same way as the Centre Pompidou. That was the beams with the many lap joints that I showed in the beginning.
Okay.
So you have single beams that are put together. I'm already a bit late in time, so I have to hurry up, but we have time for questions afterwards, I think. As I said, the straight gaps in Kristiansand also basically is a ruled surface. So you have a straight upper edge, you have a curved lower edge, and straight lines in between. In the very beginning, in the defining geometry of the project. And it has to be like that, and you have to make very clear that it has to be like that in order to be able to fabricate it and assemble it in this way, which we had some troubles there in the beginning. The next problem we're facing is basically everything that has to be digitally fabricated has to be in the model at one point. I mean, if the machine has to know where to put the drilling bit in the end, it has to know where to take this information from, and it has to be in the model, which means this is a very ugly node. I'm just showing this here. I'm not proud of it. We had to do it. You have quite a few drilling holes in every one of these nodes. Yeah. There's again the timber beam and 4 other timber beams connecting to that. Cross sections here are about 200 by 800 millimeters, just to give you an impression of the sizes. It looks a bit more beautiful when it's assembled. You don't see any steel anymore, or very, very little of it. But to get there, you have to fabricate components like this, where there's hardly any timber left. There's up to 450 machining operations on a single bit, not on this one, but there's larger ones also with lots of holes and slots and pockets and things in there. And that means at 250 components with 200 joints, you end up with about 15,000 holes in operations you have to hold in the model to then get it to the machine at some point. Yeah, until you have something like this that can be shipped off and assembled. So what are we doing? Of course, we're doing parametric models, and of course, we're programming those things in a rational and systematic way instead of sitting down and drawing 14,000 workshop drawings. But that means you also have to come up with very systematic detailing to be able to do that. And you have to come up with a rather stringent way to get from a design surface and the input you get from the engineer to the single component that you need in the end. And you end up at an information depth, at a detailing depth that it's much more than the usual BIM things that you're handling. I mean, the BIM UK protocol says that the BIM model is roughly in the scale of a 1:50 drawing. Yeah, we're working on 1:1 in the end. Yeah. As every single node is detailed down 1:1 basically, and this is what you have to do if you really want to go into digital fabrication. This is the main gap between what BIM is now and what BIM has to be if you go down to fabrication in the end. And the last bit is file to factory is a nice buzzword that's getting presented to you by everyone who wants to sell a 3D printer, but it's far from automatic as soon as you're off the beaten track. Which means it's working like this if you buy a 3D printer or a laser cutter, more or less. I mean, if you ever tried to use one of those, you know that there's still a few loopholes that you can fall into with setting up proper STL files or proper cutting paths for a laser cutter. But it's still fairly okay. Yeah, you have a CAD system, you generate whatever data you hand over to a CAM system, and the CAM system then generates whatever CNC data is needed to drive the machine. Nice with homogeneous materials like this, nice with not more than 3 axes, because then you at least have not more degrees of freedom in the machine than you have in space, which makes things a bit more unambiguous. If you have 5 axes, there are infinitely more possibilities to get to one point in space. Yeah? Usually on larger projects, you don't work on one machine, but on many. For the Norwegian project, the left one was doing the large curvy timber pieces, a 5-axis Lignamatic machine in Gosau at Bluma Lehmann. On the right-hand side, a 5-axis milling machine that did the 12,500 cladding boards. And there were 1,200 kilometers in between those, because the right one is standing in Norway, but we had to provide fabrication data to both of them from the same model in a way. You have rather complex components, which means it also makes a difference which machining operation you do at which point in the process. You have this curved things that have to be cut out. You have a little seat cut for every little cladding board in there, so that you have your nice IKEA connection that you don't have to measure, but things just click into place. But that means you have 55,000 of those seat cuts to mill. You have cuts at the ends. You have drilling holes for the connections or whatever. To know which operation comes first and which comes last is a thing that is not only depending on the geometrical properties of what can I reach, but also on the material properties and the knowledge of a timber guy that tells you, no, we have to cut off the ends first, because then the fibers in this still a bit stressed, curvy, laminated beam are relaxing. And if we do that at the very last stage of the process, we have the wrong geometry in the end, because we mill this perfect curve and then we cut the ends and the thing changes the geometry. You know this problem from 3D printing with those PLA printers, where the thing starts shrinking and warping during the curing phase in the end when it's getting colder. That's the same thing, the same problems you have in large-scale digital fabrication also. yeah, which tool to use to do different things. All those machines have up to 25, 30 different tools, and the tool changes somewhere, and the machine is getting the next tool and doing something with it. Even the raw material is a bit complex because those curvy beams, this is not the final beam, this is the raw material in a way, where those beams are cut out of. That has to be ordered 4 weeks in advance because it has to be laminated first to actually start the machine before you can do anything. And then you have things like that where you can probably find the holes automatically in there. That's easy to recognize this from the geometry. Okay, this could be a drilling hole. I'll take a 15 millimeter drill and just push a hole in there. But how to deal with those? Yeah. If you only have the final geometry of the piece in your CAD software with a feature like this, how does a CAM system find out that this is actually a drilling hole? And this little thing here was a circular pocket. It can't. Yeah. There's no way to automatically come back from the final geometry of the piece to the machining operation that you need to end up at this geometry.
Depends on the software.
Not at the failure rates you need to do this with 3,000 pieces in a very short time. That's the point. And that's where we always basically running into problems. Or we have to get to a different approach to not throw away all the information that we already had in our parametric model to come up with the final geometry, but to take all this process information over to the CAM and the machining center and say, hey, we know where this geometry comes from because we have created it in a parametric CAD model. We have to take the information that this is basically a drilling hole where 89% of it have been cut away. We have to take this over to the machining site because it would be stupid to throw away the information and regenerate it later on.
Is that a Boolean operation to make that form?
Physically, in the end, it's actually a Boolean operation, yeah.
For the parametric, did you design that or did you?
The thing is, we hardly ever do detailed 3D models like this one here, apart from when we have to show an image of it. Because it doesn't make any sense. It just gives you a headache. Because the software then comes up with, oh, there's a Boolean operation with two surfaces coming together at 0.5 degree angle. And I run into some numeric problems when I try to actually intersect that. Because if I have a bit of a rounding error, my intersection point is plus minus 2 centimeters where I want it.
With which model you work?
Mostly Rhino, actually.
Nice.
But
if you move to Parasol, they would solve it.
Right. I would then take the information with me the same way I'm taking it now, because in the end, I tell the machine, you drill a hole there, and it does it within a few tenths of a millimeter, and there is my Boolean operation. I don't need this thing other than when I make a fancy presentation with renderings in there. And then it's getting meshed anyway to do the renderings. It makes no sense. It makes much more sense to say, hey, I know this comes into being by drilling a hole there, which is a very shallow hole with a very large diameter, and 90% of it is cut away afterwards or beforehand with a circular saw blade this size. I don't need this final 3D model of the thing, actually, only for showing off. Yeah. What I need is the machining information that I can hand over to the CNC mill to do things like that. And this is what we're doing. I mean, we do sometimes, we go this way of feature recognition, getting machining information out of the final geometry, but only for very straight pieces like the one up there. Many times we're actually providing custom sort of CAM interfaces and negotiate how we transfer information between the geometrical parametric model and the fabrication model at the fabricator. So on their side, they have a CAM specialist that tells us, if you give us the information that way, we can handle it right away automatically. So we sort of build a custom interface between us and the fabricator. And sometimes we even go down and provide CNC machining code directly for the machine. So they just feed in NC data, X, Y, Z, A, B coordinates into their machine to do this. Which means your nice little linear digital chain from the beginning then looks like that suddenly. You have 4 different fabricators, probably even someone who's producing the raw material. They all need different information. And you have to talk to them to actually provide them the right things at the right time in there. So where are we going from here? Yeah, BIM to fabrication, as I said. And this is the BIM model of the Kilden project. Included everything but no facade. This is what we needed in the end. And at the moment, there's very little connection between those. Also because the level of detail that is aimed at in the BIM models up to now is not 1:1, but 1:50. So the level of detail is one of the things that we have to really take care about if we want to use BIM for fabrication. And that also means that we have to talk about scalability. I mean, from this little sphere down here where we had 12,500 components with 6 details each, we're going up to 13,000, 14,000 components in this with up to 20, or on average 20 details in this project. So basically our models are growing in 2 directions, which means at some point it's hard to handle this amount of information. The parametric model of the Kilden project contained 126 files in the end, 1 per facade element and 1 master file that hold them all together. And that sums up, including fabrication data, to roughly about 5 gigabytes of information at the end, which you have to carry around or store somewhere.
This is just the production drawings?
This is the whole thing.
The whole thing.
The whole thing. And the NC code is the smallest part of it, because that's just ASCII data that you can shrink down to nothing in a zip file. Yeah. Question: how do you actually describe parametrics? I mean, there's 2,000 connection details in this facade structure. They're all different, but they are working with the same rules. It's not about how do you program this in a software. It's about how do you describe this to sit on a desk and talk it over with an architect, an engineer, and a fabricator. Yeah. The language of architecture has evolved over a couple of 100 years. 2D plan drawings are easy to read, and you can transfer information and knowledge with that. But how do you transport a parametric detail on a 2D drawing? And that's basically the thing you need to do if you're sitting at a desk. Yeah. How do you say, okay, this needs to be bigger than 100 millimeters, this needs to be bigger than 20 millimeters, whatever, which dimension is depending on which other dimension, what's actually happening in there. Yeah. I have it in a parametric model, I have described it as a bit of code, but that's, for the time being, the only way of properly transporting this information. How do you do that? And of course, you have to actually organize the complete workflow. So engineering, detailing, sourcing, fabrication, logistics, assembly. If you look at only one point there and you optimize this one point, you may very well worsen all the other points. You have to look at the whole thing at once to find out. And you have to have the tools to do that also, which means we're sometimes actually taking tools from the software industry in terms of issue management and tracking systems to get this process done. The BIM world slowly is coming up with ideas in that direction, like the building collaboration format, where you have means of actually putting little sticky notes all over your model to say, hey, we have a collision there, hey, we have some problem there, who's going to resolve it? Just to have a management layer on top of the whole model that tells somebody who's in charge, oh, how many open issues do we have in the model? Not there yet. And this also means basically it's about working together is about really 50% of our time is sitting around tables and talking to engineers, fabricators, special planners, whatever it is, to find out how things are done. There's no way of actually controlling this from a centralistic point of view. You have to work together. And you don't only have to collaborate, which means everybody is sitting in his own little garden and throwing things over the fence in the neighboring garden. You have to actually sit in the same garden around the same table and talk to each other. That's the main point. No working any other way.
Do you Skype a lot? Or?
Excuse me?
Do you Skype a lot?
Yeah. In some, I'm just having a project right now with the French pavilion where, I don't know, I try to save those Skype protocols once a week, basically, but it's like, yeah, massive. Okay, sorry, I took far too long, but we had a few questions in between. I hope there's a few more questions left over in your heads. Please shove them over.
With the very complex joint that you showed,
yeah.
Did you design that kind of a parametric representation of that in just a very orthogonal way and then transfer that to each node?
No. That's usually the way that things are given to us. This is someone is doing very orthogonal drawings where they think they have defined the joint, and then the first thing is always to find the 5 worst cases in the whole facade and try to apply these drawings to the joint, and usually it doesn't work. Because someone, while doing this in an orthogonal way on a 2D drawing, has completely forgotten that two things are not orthogonal to each other in real, and suddenly you, for example, can't engage the joint anymore, because the engaging direction of 2 neighboring joints is not parallel, and that means you can drive it in here, you can drive it in there, but you cannot drive it in at the same time in both places, for example. Happens all the time. So we really are trying to sit together with the engineers and develop joinery in a collaborative way, where we take the part of sort of the controller, if you want to tell it in economical terms. It's like, hey, you want to do this? We check if it's actually working everywhere in the facade.
And then you tweak that.
And we tweak it as long as it works, until it works.
It means that you have a lot of, I would say, manual operation. You have a parametric model, but you have to solve different problems. That's the question. Not everything can be programmed.
Not everything can be programmed. You're absolutely right, and this is one of probably the most tricky parts in our work, is to decide when we stop automating things and doing the last 5% manually. But you still then always have to decide where the 5% start, which means, okay, I know that this is the thing that is not going to change anymore, and it's only going to happen once, and it's only 5 things that I have to do. I'll do it by hand now. And then tomorrow comes somebody and says, oh, we just changed this. And you say, okay, throw it away, do it again. If this only happens once, then it's okay. If then more changes are coming, you have made a wrong decision somewhere. And to somehow feel where this could be going to is a thing that comes with experience and only experience, and still I'm wrong too often.
With the background in computer science, I think it's so extreme that you basically have this programming really just done for this one application. Do you see any other applications in computer science where you have a similar situation, where you actually do this programming for one-off thing?
Everywhere where you're not doing consumer goods, this happens all the time.
Yeah.
Yeah. I mean, talk to somebody who's configuring, I don't know, ERP systems or whatever production systems anywhere in the world. It's a one-off. I mean, or otherwise, all those SAP consultants running around wouldn't be that expensive. This is a pretty normal thing, actually. And of course, we're not throwing away all of it. There's, of course, a certain body of knowledge that has evolved over the years that we're keeping in libraries and things, and reuse as much of it as we can to be more productive. But basically, it's a new project, and you're reusing things, but it's a completely new parametric model every time. I mean, if you do a grasshopper model, you throw it away also after you've used it and build a new one the next time, using the same components basically, but it's a new program.
But the grasshopper components are really designed to be used by a wide community of people, while your components are designed to be only used by you.
Yeah.
That's, I think, the major difference. Right?
Yeah. If somebody pays us for using it, it's no problem. But otherwise, they're staying in our office. Now, and the other thing, of course, is, I mean, it's a huge difference coming from the software industry and having worked in the software industry for quite a while. It's a huge difference if you develop a software that is used by anyone but yourself. I mean, we are quick and we are productive because we exactly know how to use the software that we've developed for this one project. And if I would have to write a proper user interface and do all the error checking, it would be 50 times the price. And there's no user basis. So it just doesn't make sense. Actually, I enjoy throwing away the software because I've learned so much during the first project that the second project is going to be more productive if I can throw it away completely and redo it from scratch.
So you've invented a new job in the chain of building construction?
Probably, yeah. I don't have a name for it. That's the problem. Marketing is a bit difficult. Yeah. Excuse me.
That was maybe not managed to follow. You said that you received some 1 to 50 scale models from where you started your interventions. Is that right?
More or less. I mean, what you usually get is a level of detail that is roughly 1 to 50 over the whole thing. Like the design input you get in the beginning. Because then my job would be done already. I mean, if there was a one-to-one model when I entered a job of every single bolt hole that's needed in the end, then I don't have to do anything anymore. The problem is more that the tools that are there now for building information modeling are not built for handling one-to-one models down to the very last thing in the end. It's a scalability problem mainly, yeah. And the other thing is, of course, a model is only as good, the quality of the model is also the problem. If you're thinking at 1 to 50, you're only modeling at the quality of 1 to 50, which means it doesn't really matter if this thing is here or 2 millimeters to the left when building the model.
I'm insisting on that point just to clarify maybe for the students that when you say 1 to 50, you talk about the amount of data that needs to be present.
Yeah. So in the digital world, of course, I mean, there's no 1 to 50. I mean, a millimeter is a millimeter is in the model basically. So it's 1 to 1 in terms of modeling scale, but it makes a huge difference in level of detail, and it makes a huge difference in modeling quality. Yeah. The quality of the model, you simply don't care about 1 millimeter left or right if you're thinking in a 1 to 50 world, because it doesn't matter. So probably, especially if you're doing it by hand, who cares if your two lines really meet in the right point or 1 millimeter left or right of that? No one actually. Yeah. Not on a 1 to 50 drawing, and this is why 1 to 50 level models look like they look now when you receive them. As soon as you really need to be within 1/10 of a millimeter modeling tolerance, because you need that for fabrication in the end, the only way is to throw away the wrong 1 to 50 models and rebuild them from scratch basically. And the only way to do that is to start with a very simple input, which means a design surface and a few axes on the floor. And then from there on, everything is built up again in a proper way where, at least in a numerical fashion, points are at the right coordinates in space. Even when I start modeling something manually, I make modeling mistakes. And you click, you don't pick the right point, and whoops, there you are. Shit happens all the time.
That's also one thing which is important to emphasize is because all the issues you have raised and all the knowledge you have introduced here to this audience, it's also highly related to your scope of work, right? What is the lifespan of your intervention? Like when do you show up during the lifespan of the project and when do you start showing up?
Yeah.
I think it's very important also for the students to realize that all these issues of bridging again a freelance process from a design model to an execution model, or what's in between, it's also highly linked to the scope of your intervention on the development of the project.
Yeah.
Or maybe you disagree with that.
No, not really. I mean, I think one of the most important things is that a good model is as small as possible. It just doesn't make any sense to put all the as much information as possible into one model. It only makes sense to throw out as much information from a model as possible and only keep the relevant information in there. Otherwise, it's going to be clumsy and too fat to stand upright in the end. Yeah, which means, and this is why we hardly ever have any 3D volumes of finished components in the model. It just doesn't make sense. It's much easier to just store the drilling axes and then hand that over to a fabrication machine that just drills a hole there with the right drilling bit and the right diameter. There you are. Why should I take care of generating another volume object and representation that I carry around with me all the time, other than for visual checking, basically? Yeah, but if I've done that, I can throw it away again.
So, what is the way of checking for, not for you, but for other people?
Yeah, that's the point. If I need the thing for visual checking by someone else or by myself, then I generate it, but then I throw it away again. Not to carry it around all the time. Also, there's, I mean, most of the quality control that we do in our project is actually coming more from the realm of software engineering than from the realm of architecture and building. So it's very hard to overlook small flaws if you do a visual checking. If you have to come up with proper checking methods to do things. Yeah, just one example, if you have a large facade where it's important that on every face of the facade surface, the orientation of the surface is right, you put on the normal vectors on every panel and make them 1 kilometer long. Then you get a hedgehog with very long spikes, and you see instantly if one of them is pointing in the wrong direction. Yeah. If you just do, if you just have the volume object of this thing, you'll never see that. Yeah. So you have to actually take a step back and what do I actually want to find out? What could be the error that is in there, and how can I find that? Oh, I come up with a checking routine. I run the script once, it generates all those, and I see it instantly. And this is this is sort of the next abstraction level on top of actual parametric modeling, is to step back into the testing also.
Coming to this, I remember you were maybe working with Java before, a few years
Long time ago.
Yes. I understand now you're working mainly with Rhino. And then I guess you encounter precision errors that come from Rhino, and you also enter all this realm of actually debugging. How much of that is part of the work that just stays in your lab? How much do you actually communicate this to architects? Because it also might bring up some design issues that are flows from the architect. How do you correct them?
Since we hardly ever have anything to do with the architect, the flow of information in this direction is rather sparse. Of course, we try to do, but I mean, there's lots of different levels to this question. One level is of, so at the moment I don't do any Java programming anymore. That's long time ago. We're actually trying to yeah, standing on the shoulders of giants is the word. We use a CAD software that's already there and is rather well known for being more or less good, but it's open enough to be extended to the point where we actually need our own tools, and this is what we're doing. This is why we're using, at this point, Rhino. If it should turn out that there's a better software to do all this, that I'm happy to start working with it at any time. It also only turns out that many of the clients we're working for are using the same tool, so it seems to make sense, at least for having proper communication interfaces back and forth at that point. And then precision is mainly a problem when you start doing things without knowing what happens in the background, which means we are programming parametric models on the firm basis of vector math and trying to use as little numerically problematic functions in there as possible, which means finding intersections between 17 different NURBS curves and things like that is something that has to be broken down into similar tasks that can be solved on a proper mathematical basis to come up with models that work in a year from now still. And that's, I think, the point where I would be very interested to have a discussion with Bernard afterwards, is how you care about geometry. Because the computer doesn't do it for you. The computer is probably able to resolve geometrical problems on a numerical basis up to a certain degree of complexity and precision. But it's much easier to build proper parametric models if you're able to do a bit of vector math and come up with proper definitions of what you actually want to do, where you know that they'll be working also in difficult situations. And that is where I think, unfortunately, I know that many architects don't really like mathematics very much, but there's no other way of doing that.
Wait for the next generation.
I'm hoping for you to change that. No, it's really a point. I mean, it's like I've been sitting in geometry courses at architecture schools myself, and I always found it actually very entertaining, whereas my colleagues always found it cruel. And that's probably the main difference.
You said you come into the projects quite often, even when it's already on fire.
Yeah.
Which I really believe. There would be a desire of getting into the project before it's on fire.
It would be nice, of course, but the problem is that since we are a consultancy, the only thing that we can sell is knowledge, and if we give it away for free, we can't pay our rent. And on the other hand, knowledge is the only thing that is needed early on in those projects, but there's never budget for that. And this is the clash of cultures that we have here, is as long as it's perfectly normal to spend 30% of the planning budget on the construction site, it's also perfectly normal that there's no budget to spend early on in the projects on yet another consultant like myself.
I mean, if you wouldn't care about the architectural quality of it, you might not mind coming in when it's already on fire.
Yeah.
The more you come in early in the stages,
it would be helpful once in a while. Yeah, I think so too.
You become more of an architect, don't you?
I mean, there is a reason why I studied computer science and not architecture as a main subject, because I think I wouldn't be, probably, at least I wouldn't be a good designing architect. I'm more of an engineer problem solver in my mindset, and that's perfect. I'm perfectly happy where I am. But I would be even more happy if I could use this knowledge earlier in the project to prevent people from running into the completely wrong direction.
It's the same for, I would say, also for engineering.
It's the same. It's actually the same. The only problem really is that I don't really have a name for what I'm doing, and I'm not on the standard list that gets ticked off whenever a planning team is put together. I mean, engineer checked. Building physicist checked. Geometry expert. Why a geometry expert?
increasing because of the lifespan of the project. Investments are growing through the lifespan, so at the beginning there is a very low budget, and then it's more and more invested into, it's more invested construction-wise. But the thing is that the more you make design changes through the lifespan, the more expensive and cost you have on site. And so that's also the reason why people jumping into development design is to say, oh wait, we're going to have huge problems, we need to hire people to either transfer the knowledge or to embed knowledge into the model, like the messing work that Fabian is doing. And unfortunately, it's mainly, most of the time happens, I mean, correct me if I'm wrong, most of the time happens from the PD phase, right? And most of the, not most, but a lot of big design firms have understood that and implemented this in-house, like for example Foster's, SOM, they try to build up this knowledge, to capitalize this knowledge, and hire less and less consultants for that. But the thing is that the premise also come of scale, like for companies, design offices, I mean, or even some engineering companies who don't have a huge scale or are not used to deal in a frequent time with big projects, investing, having this kind of investment into knowledge is very hard as well. And it's not part of the culture to invest a knowledge which will be important for the next phases, like something that they will have to deal after. It's not part of the culture, which is a bit a pity, because they don't have this anticipation of what will happen, even if they are very experienced offices. Your predecessor, as a lecturer here, was the principal of Snorreta in Innsbruck, not far from here. And yet they are very good designers. But they were still using the same programs that they don't invest into this kind of knowledge in house as well. And they found themselves on site with the same typical problems.
Yeah. I mean, the problem really is, as you say, it's an investment, and that means if it's an investment, it has to pay off at one point. And the big problem with the building processes and the fee structures that we have is that it doesn't pay off because the one benefiting from it is not the same as the one investing in it. Which means if you invest a substantial amount of money, budget, fees, whatever you call it, in an early design phase to solve problems that would probably occur later on, the only thing you're saving is either money from your client or money of the poor contractor that is hopefully doing it only once in the end instead of twice, which would be usual. But you don't get anything back from that as an architect in the fee structures that we have right now. So we're in the lucky position to lean back and say, hey, we wait until it's burning on construction site, and then they'll call us, and then we still would ask our fees because we don't work for free and they have to keep their deadlines. Bad luck. Which is, of course, if you look at the whole process and the productivity in the building industry is a nightmare. Yeah? Absolutely agree. And if you look at the productivity figures in the building industry as compared to the productivity figures in the consumer goods industry over the last 20 years, you would recognize that while the one has gone up by 175% since 1991 in Germany, the building industry has gone down by 1% over 20 years. Meaning you still get the same value for money that you've gotten 20 years ago, while in other industries you get almost double the value for the same money.
But precisely because in the building industry we do not use the tools that they are using in the rear industry.
No, because we don't using the processes that they're using and the methods.
Already, yes,
Yeah.
exact models and all of these things.
Yeah, but I really think that it's not about the technology. It's mainly about the processes and the workflows and the methods and the mindsets of the people doing that and the structure of the industry, which is of course highly fragmented, and you have tons of stakeholders in every project, and everyone is trying to get as much productivity out for his company, but not necessarily for the neighboring company that's coming after him on site. And of course, very rarely for the good of the overall project. Yeah. Naturally, because we're living in a capitalistic world, and I have to pay the rent and the wages at the end of the month, I have to look after my own productivity, not necessarily after the productivity of the architect or the fabricator or the engineer. And this is different in other industries, of course, and has equal flaws. I mean, I don't want to be delivering goods and parts for iPhones to Apple, because I know that they have rather tough guys sitting there buying things and negotiating budgets. The same thing. Someone's basically gonna bite into the grass in the dust at some point. And I also perfectly know that I won't be the guy changing the workflow model of the building industry. But you probably are in 10 years from now.
Is there any questions?
Yeah.
I think on the project or in wood, do you consider to sometimes change the material?
This is a mistake, basically. It was never planned to be only timber project. It just turned out to be. The venture as such set out at a point where we were completely material independent. It just turned out that timber is a great material to build around curves. Mainly due to two reasons. One is the material properties which make it very easy to be machined, but at the same time are still being used as a structural material. And the other point is that there is not really a timber industry, because the industry is basically built from very many very small companies, but there is a high-tech timber industry out there which is highly digitized already, or has been even before we entered the image. So the machines and a lot of knowledge is already there. It's just used to do straight things. And the step for using the same machinery and the same knowledge to do curvy things is smaller than if in other industries. Steel beams are very hard to get into the right to get bent into the right shape precisely. And that's the point where there's so many timber projects in this curvy realm. And of course, timber is a green material, which is very important, or gets more and more important at the moment. Half of it is actually marketing speech, but still, it's a very interesting material to work with, also in terms of sustainability and other things. But I'm happy to work in glass, steel, reinforced concrete, whatever you have, we do it, if you understand what the problem is.
Like the little guy sitting over there.
What?
Like the little guy sitting over there.
Yeah.
Do you do anything with additive manufacturing?
Not yet, really, no.
Is there an interest?
Yeah, as soon as someone comes up with something that works on an industrial level, definitely yes. But apart from now, there's very few ideas that really develop into a direction that could be exploited on a reasonable scale at the moment.
Is there anyone close that you've seen?
I mean, additive manufacturing is always a question of scale and resolution. I mean, as soon as you start using bricks as your additive building material, you're getting reasonable sizes and reasonable building times. So I think it was a smart move of Grammatio and Kohler to use their robot for stacking bricks on top of each other. But it gives you a resolution of roughly 10 centimeters that you can work with. As soon as you need something with a higher resolution, you're running into scalability problems, unfortunately. And I'm looking forward to see what's coming out of that. But I mean, dust printing at a larger scale is just has to speed up tremendously to be interesting for the building industry. And the same with all those concrete nozzle whatever things. I mean, you have to imagine that I actually don't really believe in on-site digital fabrication that much. Yeah, because the equipment you need to do a proper job is expensive, it's sensitive to environmental conditions. The machines used to do the project that we've done, they have their own factory hall. And the factory hall is not a small hall, but there's a machine in the middle and there's 20 meter on one side and 20 meter on the other side, just to take a 20 meter long beam, drive it through the machine and out on the other side again. And the thing has to be level, it has to be stable, it has to be supplied with a substantial amount of electrical energy. You have to have an operator right next to it, which is highly skilled and expensive. You have to have a complete supply chain that's able to supply raw material to be fed into the machine. There's also post-processing where you need people to take the things out of the machine and probably put little plugs into dowel holes and stuff, whatever. This is all working perfectly fine if you have a controlled environment somewhere out in the eastern part of Switzerland, on the green meadows with cows around it and everything. And then you put the finished things in a container, ship them to South Korea and put them together. Works perfectly well. I wouldn't imagine what it would take to actually take this machine and put it somewhere on site. Alone to get it running there would take half a year. Because that's what it takes to get a machine like this running in a real industrial environment too. It just doesn't make too much sense. Yeah. From my point of view, the idea is prefabrication as much as possible, as smart as possible. I mean, of course, you can build your own shelves with a circular saw in your basement, but you can also go to IKEA, have it prefabricated. What's quicker? What's more efficient? What's more fun is a different question.
Well, thank you very much.
Welcome anytime.